zinc in H plus for CH, and this is Wood's reaction. CH3, and this is a sodium salt of carboxylic acid, which on decarboxylation. Ready? The first one. Right? This is the alkyl group, right? Fine. So, up to this much, right? This much. Followed by one, two, three, four. 1, 2, 3, 4. This is okay. No. Hydrogen added in red phosphorus. A will be this is a monovalent group which is replaced by hydrogen. Normal butane. Normal butane on bromination to bromo. Okay, and you have N-propyl chloride, which on Wood's reaction forms normal hexane. Normal hexane on aromatization. Benzene. Okay, the very same N-propyl chloride on reaction with zinc. Okay, so forms propane. Propane on chlorination forms isopropyl chloride and normal propyl chloride. Ready? The very same normal propyl chloride with the magnesium dried forms Grignard, which on treatment with the methanol, the forms propane. Propane with the CH3 or this. Okay. Ready? Preparation of alkene. The first method is over. Ready? The second method, internal Kolb's reaction. Internal Kolb's reaction. Internal Kolb's reaction. You are familiar with internal Kolb's reaction. Internal Kolb's reaction. Internal Kolb's reaction, you know Kolb's reaction. Let we have sodium succinate. Sodium succinate, which on electrolysis, what happens? This replaced to form a bond. Agreed. CH2 double bond CH2. Okay. So you obtain alkene. Ready? I have methyl sodium succinate. Methyl sodium succinate. This is the compound. One nitrogen replaced by methyl. We can ready the product. Okay. Copy that. Then the next is dimethyl sodium succinate. Dimethyl sodium succinate. Dimethyl sodium succinate. Okay. So you simply replace the CO and put a bond. Okay, you are familiar with the Corpus electrolysis. So the internal Corpus electrolysis from alpha beta position leads to the formation of alkene. So can be considered as a preparation of alkene. Okay. So what about the product here? This is replaced to form the propane. Fine, propane. Okay. Propane. What about the next? Butene, right? 2-butene. Agreed. CO replaced and make a bond. Okay, like that. Here it is. Here it is. Cyclohexane. Okay. So simple method because you already know the reaction. Okay. So that's easy. Okay. Now we are moving to the elimination. Elimination from alpha beta position. Okay, alpha beta elimination leads to the formation of a double bond. Any molecule have an alpha beta elimination that leads to formation of, there is one elimination become alkene, two elimination it become alkyne. Okay, so we have two important elimination which is discussed in your haloalkane, say beta elimination in presence of alcoholic AOH, and the second one dehydration of alcohol. These two are important eliminations where the product is alkene. So the next reaction is beta elimination. Okay, beta elimination. Put as a heading beta elimination. Beta elimination. Okay, beta elimination. The general logic of this reaction is we are given with a saturated compound where there is a functional group on a particular carbon. Let that carbon where the functional group attached is said to be alpha, and the nearest carbon is said to be where we have hydrogen. Okay, so on treatment with a particular reagent, okay, what happens? Elimination of the functional group from alpha and hydrogen, corresponding hydrogen from beta to form a new bond. Then the molecule become unsaturated. What do you obtain? Alkene. So this is the general idea. Okay. If the function group is halogen, then the molecule is said to be alkyl halide. Then the elimination is said to be dehydrohalogenation. What do you mean by hydrogen halide? HX. So if the eliminated molecule is HX, then it is said to be dehydrohalogenation. If the function group is OH, then the molecule is a alcohol, or the elimination is H2O, said to be dehydration. So we have two different categories here. Ready? So show the general case. general reaction. Okay. Category, that is dehydrohalogenation of alkyl halide. Okay, dehydrohalogenation means removal of hydrogen halide. That means HX. Removal of HX. Okay. Listen. The very same reaction. First of all, the elimination may be through three different mechanisms. Elimination have three different mechanisms. The first one is elimination unimolecular, said to be E1, just like your SN1. If you are familiar with SN1, nucleophilic substitution unimolecular. Like that, there is an elimination also, said to be elimination unimolecular, E1. Okay, like your SN2, there is E2 also. E2, elimination bimolecular, and then another different mechanism said to be elimination unimolecular in conjugate base, E1CB. So actually there are three different mechanisms, E1, or it may be E2, or it may be E1CB. Or CB stands for conjugate base. Okay. Unfortunately, we can't predict the mechanism if the beta elimination is in the case of alkyl halide. We can't predict the mechanism. But if it is in the case of alcohol, we can predict it as E1 mechanism. Okay. Here we can't predict the mechanism. Okay. So you simply remove the halogen from alpha, hydrogen from beta. That's the only way to design the product. Okay, but in case of alcohol, we can predict it is in a even mechanism. So the questions will be answered based on the mechanism. Okay, here we can't predict whether the mechanism is E1 or E2 or E1CB. But if it is mentioned in your question, then only we can choose. Okay, otherwise we simply remove this and make a bond like this. Okay, if we have more than one possibility, then we can predict the major. If we have more than one possibility for this elimination, which means more than one elements are formed, then we can predict the major and minor. I think you are familiar with that, based on Chase approval. Okay, but we can't predict that whether it is E1 or E2 or E1CB. Dehydrohalogenation of alkyl halide may follows E1, E2, E1CB. Okay, if it is mentioned in your question, then you have to do like that. Okay, otherwise you simply remove this from alpha and beta. And in the next case that follows, which means that in the case of dehydration, it is sure that it follows E1 mechanism. Okay, which means something like a SN1 mechanism, which means in the first step there forms a carbocation. Okay, so here also there forms in E1 mechanism also forms a carbocation. Then you have to rearrange the carbocation. So you should be well familiar in the rearrangement of carbocation. Then only you can do the dehydration. Here there is no problem. Okay, fine. So this is the case. Mechanism may be E1, E2 or E1CB. And this is for any one. This is only for here HX is removed. Okay. Okay. Show this much. I'll give you examples. The mechanism may be E1, E2 or E1CB. Okay. SN1? SN1. SN1 means you are given with the alkyl halide in presence of a polar protic solvent. Polar protic, which means a solvent which furnish H plus, where the halogens removed from the molecule to form planar carbocation. Okay, here the reaction possible. Rearrangement is possible. Then, after the rearrangement, there is an attack of nucleophile. Attack of nucleophile. Either it may be through front side or it may be through back side. Okay, if it is through front side, what is the specialty? You obtain a nucleophile which is in the same configuration of your alkyl halide, which is in the same position of your alkyl halide. So that product is said to be retented product, and the process is said to be retention. Well, if it is through a backside attack, then it would be like this, inverted product. This is said to be SN1 mechanism, which is given in your haloalkanes. I think you are familiar with that. Okay, what is the change in E1? This is SN1 mechanism. So you can very well compare the E1 mechanism with the SN1. That means I have an alkyl halide like this. Ready? Alkyl halide with the beta hydrogen. Okay. Protic solvent. Treatment with the polar protic solvent. Listen here. Listen. Treatment with the polar solvent. So the forms a carbocation. The very same X. The forms a carbocation where rearrangement is possible. Okay. Here the rearrangement is possible. So you should know what is the rearrangement. Rearrangement, there may be an elimination of proton from the alpha portion of carbocation. After the rearrangement, there is an elimination of H plus. Here it is a substitution. Here it is a elimination. So what happens? If H plus gone, then this electron pair jumps to here to form the and this is said to be E1 mechanism. E1. Okay. So in SN1 and E1 mechanism, the first step is the formation of carbocation. But in SN1 mechanism, the second step is a substitution. Okay. Substitution. But in E1 mechanism, the second step is the elimination. Okay. So it is clear that in E1 mechanism, the two steps are the cleavage of bonds, right? The first step, carbon halogen bond cleaved. The second step, carbon hydrogen bond also cleaved. Okay, so if vibrational system increases, the cleavage will be favored, which means temperature increases, there is a chance for elimination. Okay. Okay, what about the SN bond? First step is a cleavage of bond, but the second step is a formation of the bond, right? Here the second step is also the elimination. Okay, so usually as temperature increases, there is a chance for elimination. There always a competition for elimination and substitution. Okay, because elimination is always in presence of this H plus is abstracted in presence of what? Base. Okay, base is nothing but it is a species which can donate electron pair to H plus. Base is a species which can donate electron pair to. If this is a base which is ready to donate electron pair to H plus, then H plus is abstracted from this. Okay, the necessary electron for H plus given by the base. So H plus is abstracted so that the bond jumps to here to form the alkene. Okay, but what about a nucleophile? A species which is ready to donate electron pair to electron deficient carbon. That is a nucleophile. This is a nucleophile which is ready to donate electron pair to electron deficient carbon, which means OH minus can act as base as well as nucleophile. OH minus can donate electron pair to electron deficient carbon. If so, it acts as a nucleophile. If OH minus donate electron pair to a electron deficient carbon, then the OH minus which act as a nucleophile. At the very same time, the OH minus can also donate electron pair to what? H plus. So where it acts as a base. So there is a competition always. Okay. From the first step, there forms a carbocation. Okay. In the second step, if the base or nucleophile both are same or both have same property. So in the second step, if the species, then maybe can call it as a base of nucleophile. If that donate electron pair to this electron deficient carbon, then substitution taking place. Ready? Where if it donates electron pair to H plus, then the elimination takes. So there is always a competition between elimination and substitution. So we can't predict whether the elimination or substitution, but we have an idea. In elimination, the two bonds are cleaved. So as temperature increases, there is a chance for elimination. Okay. So in every substitution reaction, if the elimination is always powers if alkyl halide is a tertiary. Usually the elimination is found in presence if the alkyl halide is a tertiary. Okay. So there is in every substitution reaction there is always a competition with the elimination. Okay, because it is based on it can be explained mechanism. Okay. Williamson synthesis a reaction, I think you know. Okay, in Williamson synthesis, if the alkyl halide is a tertiary one, you obtain alkene, not either. Okay, either formed by substitution or is alkene formed by elimination. I think you are familiar with that. Okay, if you have a tert-butyl halide along with the sodium alkoxide, for Williamson synthesis, your product will be isobutene, an alkene. Because if the alkyl halide is tertiary, there is a chance for elimination. Because the very same sodium alkoxide, where the base in Williamson synthesis is a sodium alkoxide. If the alkyl halide is a primary, this acts as a nucleophile. It donates electron pair to electron deficient carbon. Where if the alkyl halide is a tertiary, it acts as a base. It donates electron pair to H plus to form the elimination. Okay. So once you know the mechanism, then you can explain or you can realize why it becomes elimination or why it becomes substitution. Okay. So this is the mechanism E1. Ready? Like you know the mechanism SN2. What about SN2? In SN2, this is a single step reaction, right? Okay. Where nucleophile approaching to backside where the halogen leaves from here. And this is in presence of a polar aprotic solvent. Acetone is a polar aprotic solvent. Polar aprotic solvent means there's a polar solvent but not able to furnish H plus, not able to supply H plus. Usually a compound which acts as a polar solvent where the H plus is in electronegative atoms. Electronegative atom. H2 is a polar solvent. Polar protic solvent, where the hydrogen H plus is in. What do you mean by polar protic solvent? A solvent which can donate H plus. For the donation of H plus, the H plus should be in a more electronegative atom. Okay, so H2 can act as polar protic solvent. NH3 can act as polar protic solvent. Alcohol can act as polar protic solvent, where the H plus is in more electronegative atom. But acetone, which acts as a polar aprotic solvent. Why? Hydrogen is in carbon. Carbon and hydrogen have comparatively same electronegativity. There is not much electronegativity. Okay. So, so this reaction is in presence of polar aprotic solvent. So that was bond making and breaking to form inverted product. Why the backside attack? That is for the smoothness of leaving. Okay. If it is through front side, then there may be a disturbance. Okay, because the leaving from the front side, so that the attack should be through back side. Okay, otherwise there is a controversy or a disturbance in this reaction. What about E2? E2. This is SN1, SN2. You obtain inverted product since the attack always from backside. Like that, there is an E2 mechanism. E2 mechanism, only a simple step. A simple step. Where you have a base. You have a base. That means the leaving of halogen. Listen here. Leaving of halogen and leaving of hydrogen. The hydrogen and halogen should be anti-periplanar. Something like a backside attack. Here the leaving from here and attack through the backside, right? Like that. There is a chance for hydrogen here and here, right? Okay. But if the mechanism leaving halogen exists in this plane, then the leaving hydrogen through the base should be in the opposite plane. They should be opposite plane. Okay, so this lift form the bond, and this is a mechanism in a single step. Okay, halogen leave from a plane where hydrogen leave from the opposite plane. Okay. So in the case of elimination of alkyl halide, we can't predict whether the mechanism is E1 or E2. E1C is a rare mechanism. You should have a clear picture about E1, E2, SN1, SN2 at least. Okay. Halogen and hydrogen be anti-periplanar, which means they are in opposite plane. Okay, so our discussion is the dehydrohalogenation. Both the reagents are either alcoholic potash, sodamide, or alkoxide ions, strong bases or simply bases. Okay, in presence of base, the elimination favors. Okay, so these all are the reagents. Show that. Now we can discuss some examples. Listen, what about the first? What the reagents are? Okay. No reaction. Why? No beta hydrogen. No beta hydrogen. Okay. What about? I think you have an idea. Halogen from alpha, hydrogen from beta, and I make a bond between alpha and beta. If more than one possibility, then show the or. Okay. So this is alpha, beta. So what about the product? CH2 double bond, CH2. Agreed. Oh, is it okay? Alpha, beta. CH3, CH double bond, CH2. Okay. Listen. So alpha, beta, beta. So there are two different beta. There are two different beta, but it is identical with respect to the alpha, right? Agreed. This is your alpha. Agreed. Okay. With respect to this alpha, this beta and this beta are same, right? So there is only one. Okay, there is identical chance. Actually, there is two chance, but both are same. So we have 3 hydrogen here. So a single hydrogen enough for the elimination, and you obtain like this. That is propene. What about here? Alpha, beta. One beta is there. We have hydrogen here. Therefore, butane. Butane. Show up to this much. Ready? So from the next molecule onwards, then we have two different possibilities. Okay? So we have to predict which one is major, which one is minor. Listen. This is alpha, beta, beta. Well, these two betas are entirely different with respect to this alpha, right? So exactly we have one possibility. What are they? From the terminal beta hydrogen, CH2 double bond, CH2, and this is butene, right? Sorry, butane, where this terminal double bonded carbon have two hydrogen, and this carbon have a hydrogen followed by ethyl group. Ready? The molecule is butane. What about the next chance? Elimination may be through this. Okay. So CH3, CH double bond, CH3. Okay. Let me cross the molecule. CC double bond. I have a methyl hydrogen, methyl, agreed. Okay. So according to Seitz's rule, is the major product. Okay. And you know the rule, more substituted alkene will be major. More substituted alkene will be the, more substituted alkene means listen here. Okay, substitution is not criteria. More stable alkene will be the major product. That is the actual idea of Seitz's rule. Okay, more stable. If we have more than one chance, then which one is the most stable alkene? That will be the major product. That is actually Seitz's rule. He said that more substituted alkene is the major product. More substituted alkene means substitution means a double bonded carbon which is attached to another carbon. Okay, here the double bonded carbon attached to two hydrogen. That is not considered as a substitution. Okay, so in this double bond carbon there is no substitution. In this carbon, hydrogen is not considered as a substitution. But there is a substitution to CH2, right? Okay, what about the CH3? CH3 is a substitution of CH2, not the double bond. Okay, so only one substitution. Well, the substitution is nothing but it is alpha carbon, right? Substitution means that carbon is a alpha carbon. So more substitution means more alpha carbon, more hyperone. That is a correct logic. Okay, greater the substitution, which means greater the number of alpha hydrogen, or greater the number of alpha carbon, greater the number of alpha hydrogen. If alpha hydrogens are relatively greater, what happens? The number of hyperconjugate structure of that alkene increases. So the stability of that alkene increases. Okay, so according to Seitz's, more substituted alkene will be the major product, which means that more substituted alkene means alkene of more alpha carbon, alkene of more alpha hydrogen, alkene of more hyperconjugative structure, alkene of most stability. Okay, so here there is two alpha hydrogen, two hyperconjugative structures are possible. What about the next? What about the butane? This considered as a substitution. That means alpha. This is not, this also, but this considered as a substitution. So actually in a substitution manner, two substitution, or in alpha hydrogen concept, there is actually 6 alpha hydrogen. So this is the most stable alkene. That's why this is a major product. Okay. So the actual meaning of Seitz's rule is more substituted alkene is a major product, means more stable alkene will be the major. Okay. Substitution is not a criteria always. Stability is a criteria. That will be clear from the other examples. Okay. Fine. So show that. Okay, you can write sets of rule. Sets of. Okay, more substitute. Sets of rule is used if there is two different. If there we have two different beta hydrogen, which means two different alkene formed. So choose the more substituted alkene with the will be the major. Okay, more substituted alkene. The meaning is actually more stable alkene. Okay. Ready? So let's have a looking for possibilities. So this is alpha, beta. Okay. So if it is from this beta, a bond will be here. If it is from this beta, a bond will be here. Okay. So the chances for the formation of alkenes are either like this or like this. Agreed. Okay, which one is the major? What about the alpha? This is alpha, this is alpha, this is alpha for the first 9 alpha. What do you mean by alpha? A single bonded carbon which is just nearer to double bonded carbon. Okay, ready? So 9 alpha hydrogens are there. So 9 hyperconjugate structure, most stable. Okay, what about this one? This is a double bonded carbon, or this one. To the right there is no carbon, so for this is alpha carbon, only one hydrogen. Okay, so this is more and more stable than this one, so this will be the major product. Okay. What about the next molecule? It's in a cyclic ring. Okay. This is alpha, beta, but the two betas are identical with respect to alpha, so only one possibility. So there is no competition, so there is no sets of rule. Okay. Okay. What about the next? This is alpha, this is beta, this is also beta. The two betas are entirely different, and the two beta have hydrogen, right? Here one hydrogen, here we have two hydrogen. Fine. So elimination may take place. To form, if it is from the top beta, alkene will be like this. From this beta, it will be like this. Agreed? If it is from the bottom one, it will be like this. Which one is more stable? Second one. Okay. What about the alpha? This is the carbons. Alpha. Or we have 2, 1. How much alpha hydrogen? 1 is here and 2 is here. 3 alpha hydrogen. Agreed? What about this one? This is alpha, this is alpha, this is alpha. They all are alpha carbons, but you are asked to find, or you have to count the alpha hydrogen. Okay. 3 hydrogen, 2 hydrogen, 2 hydrogen, 7 hydrogen. But the first one have only 3 hydrogen. So which one is more stable in second one? Okay. Here also have 2 different beta hydrogen, right? The beta hydrogens are different because this is an allylic beta, allylic beta hydrogen, but this is simply a secondary beta hydrogen. The 2 beta hydrogens are entirely different. Okay. With respect to bond, with respect to this beta and this beta different. So we got 2 different possibility. What are they? First one. Right, this is the first one. From this beta, this is the second one. So, which one is more stable? First one is more stable because this is a conjugated one. You know benzene. Okay, benzene. This is benzene, fully conjugated ring, right? If this bond is erased, the molecule will be like this. This is a conjugated one, the conjugation. Okay, alternate multiple bonds. So this can show resonance like this. Okay, but here there is no resonance. This is a non-conjugated. So substitution is not the criteria. Stability is the criteria for designing the major product. Okay, which one is the most stable? That one will be the major product. Okay, keep it in mind. So this is conjugated, most stable, then this product will be the major. Okay, the first criteria is for conjugation. First preference is for conjugation, then only we consider the alpha hydrogen. Okay. Resonance have greater effect than hyperconjugation. So if there is conjugation, give the preference for conjugation, first comparing the stability. Okay, then only you can compare the substitution. Okay, what about the next? This is beta, this is also beta, right? Agreed. A chance for like this. Which one is the major one? First one. Why? First one is the conjugated. Double bond, single bond, double bond. The system is conjugated system. Okay. Alpha, beta, beta. The very same effect. This is the first one for first chance. Second chance. Agreed. This will be the major. Because this double bond is in conjugation with this ring, okay? That's a benzylic double bond. Double bond is in conjugation with the ring. Why? Double bond, single bond, then double bond, single bond, double bond, okay? So that is in a conjugation.
Cross conjugation increases.
Cross
conjugation stability for
cross conjugation ഉണ്ടാവും അവിടെ. എങ്ങോട്ടാ? ഇവിടുന്ന് അങ്ങോട്ടോ? ഇത് ഇങ്ങോട്ട് വരുമ്പോൾ ഇങ്ങോട്ടോ? ക്രോസ് കോൺജുഗേഷൻ ഉണ്ടാവും, പക്ഷേ സ്റ്റെബിലിറ്റി അത് നിന്റെ കേസിൽ ഇങ്ങനെ എക്സ്പ്ലെയിൻ ചെയ്യുന്നുണ്ടോ? ആ, അത് ഇപ്പോൾ ക്രോസ് കോൺജുഗേഷൻ വന്നു കഴിഞ്ഞാൽ റിയാക്ഷൻ്റെ റേറ്റ് ഒക്കെ കുറയും. നമുക്ക് നടക്കേണ്ടത് ഇത് റിങ്ങിലേക്ക് കോൺജുഗേറ്റ് ചെയ്യാലോ, തിരിച്ച് കോൺജുഗേറ്റ് ചെയ്യാലോ. അപ്പോൾ അതിൻ്റെ റെസൊണൻസ് സെക്ഷനാണ് അവിടെ കൂടുതലായിരിക്കും മറ്റേനേക്കാൾ. റിലേറ്റീവ്ലി മറ്റേനേക്കാൾ സ്റ്റേബിൾ ആയിരിക്കും ഇത്. ആൽഫ അടിച്ച് നോക്കിയാലും അങ്ങനെ തന്നെ ആയിരിക്കും. ക്രോസ് കോൺജുഗേഷൻ വേറെ കേസിലാണ് നമ്മളിപ്പോൾ ഉപയോഗിക്കുന്നത്. അപ്പോൾ ആസിഡ് ഡെറിവേറ്റീവ്സിൻ്റെ റിയാക്ഷനിൽ ഇത് ഇങ്ങോട്ട് ചെമ്പത് മൈനസ് പ്ലസ് ആകുമ്പോൾ ഇങ്ങോട്ടൊരു ക്രോസ് കോൺജുഗേഷൻ ഉണ്ടാവാം. അപ്പോൾ ഇപ്പോൾ ഇലക്ട്രോഫിലിസിറ്റി ഇല്ലാണ്ടാവും, അപ്പോൾ റിയാക്ഷൻ കുറയും. അതുപോലെ ബീറ്റ ഡൈകാർബണിലിൻ്റെ ഈനോൾ ഫോമിലൊക്കെ അസറ്റൈൽ അസറ്റോൺ എന്ന് പറയുന്നുണ്ട്. അസറ്റോ അസറ്റിക് എസ്റ്റർ ടോട്ടോ മറിച്ചത് പറയുന്നുണ്ട്. ഇവിടെയൊക്കെയാണ് ക്രോസ് കോൺജുഗേഷൻ വഴി ഡിസ്റ്റർബൻസ് ഉണ്ടാവും. ഇവിടെ ആ ഫസ്റ്റ് രണ്ടും കമ്പയർ ചെയ്യുകയാണെങ്കിൽ തന്നെ ഫസ്റ്റ് വൺ തന്നെയാണ് സ്റ്റേബിൾ ആവുക. ആൽഫ അടിച്ച് നോക്കിയാലും എങ്ങനെ നോക്കിയാലും കഴിഞ്ഞില്ലേ? The last one. This is alpha, beta, beta. Okay, one is this one. Second is this one. This is both are different. Okay, it is discussed in the yesterday's class, cis and trans. Okay, but the cis form is more stable here. Okay, from C3 to C7 only cis. This is the stability of cycloalkene. Alkene. The geometrical pattern of cycloalkene. Already told you that cycloalkene of carbon 3 to 7 only cis form existing. That's why there is no geometrical isomerism. It is mentioned in the yesterday's class. Okay. From 8 onwards, cyclooctane can exist as cis and trans. This is cyclodecene. Have cis and this is what? Cyclodecene. Cis configuration, trans configuration. From 8 to 11, cis is more stable than trans. From 12 to above, it is experimentally find that trans is more stable than cis. So this of carbon 10, right? So cis more stable than trans. Okay. Write a note point. If dehydrohalogenation in presence of bulky base, then Hoffman, HOFF, then Hoffman's elimination may take place. Hoffman's elimination may take place. Okay. First of all, Hoffman's elimination may take place in bracket reverse of Seyss. Hoffman's elimination means that it's a reverse of Seyss. Less substituted alkene will be the major product. Okay, in bracket reverse of Seyss. That's the reverse of Seyss. Okay. First of all, you have to know which one is the bulky base. Bulky third butoxide ion CS3, CS3 O minus. Okay, or triethylamine. Triethylamine means we have ethyl group of number 3 on a nitrogen. This is a bulky base. Okay. Or lithium diisopropyl amide, abbreviated as LDA. Okay. Lithium diisopropyl amide. So nitrogen have 3 valency, where 1 H plus is replaced by Li plus. Okay, so Li plus and N isopropyl, diisopropyl minus, lithium diisopropyl. These are the common bulky base. Okay, well, the most important one is this one, or most frequently asking one. So this is your 2-bromobutane ready, and we have 2 possibility. But if the elimination presence of a simple base like ethoxide ion, what do you obtain? Butene as a major product, and this is Seyss of elimination. But if it is in presence of a bulky base, your major product will be good 1 in, and this is said to be Hoffman's elimination. Okay, I think you know the mechanism. From the second step, or the base have a role to abstract the H plus, right? Okay, to abstract the H plus. Listen, here actually two chance for abstracting H plus. In case of a bulky base, the chances for abstracting H plus is either this one or this one. But this is a crowded base, right? Bulky base. So it is very difficult to abstract H plus from the crowded space like this. So it is very easy to abstract H plus from the end. Okay, so bulky base are usually abstracting the H plus from the non-crowded space. So it may lead to the terminal double bond. So it's result to the formation of a major product of less stable alkene. Okay, that's the reason. Ready? So bulky base abstract less hindered proton. That's the explanation. Bulky base abstract less hindered proton. What is this one? What is this one?
I did not bring notes. I did not bring this classwork, sir.
I can't understand what.
I didn't bring classwork.
Once again.
Didn't bring these notes.
Where? From where?
Some homes.
From last year.
No, sir. Some homes, sir. I go to yesterday I was trying to make it.
There is no note for you.
I have it, sir, in the home.
Do you have the note of this topic?
Yes. It's in home. Yesterday I was trying to make it.
How? This is taking this moment, right? Oh, you have to copy. Fine. Okay. Note is an important criteria. Ready, especially for organic. Okay. Fine. Leave it. Move to the next. Wait. One more question. How many possible alkene are there when how many possible alkene are there when two bromo treated with alcoholic carbonates. Come here. Ask sir. Okay. Can you copy? It is start writing. Okay, this okay, how many possibilities? No, 3. If it is 2, then why I include this question? Okay. Well, the first possibility, that is pend 1 in, right? Pend 1 in. And the second possibility, pen 2 in. Where the pen 2 in can exist as cis and pen 2 in can exist as cis and so if the question is maximum possibility, then you have to consider the stereo arrangement also. Okay, actually 3 products are there. Where transform is more stable. This is trans, this is cis, agreed. You know the shape of cis, the shape of trans. Where transform is more stable. In case of normal alkene, acyclic alkene, transform is stable than cis form. Okay, I'll give you the explanation once the chemical property of alkene is reaching. Okay, when I was in a okay, this is more stable because due to less repulsion. So the major product in the elimination of 2-bromobutene is, sorry, 2-bromopendene is transbutene, sorry, transpend-2-ene. Okay, you know, pentuene is most stable, where the trans is most stable. Okay, so the major product is transpend-2-ene, and the possibilities are 3 actually. Okay, fine. Enough. Next, dehydration. Before that, you should have an idea about the rearrangement. Okay, then only hydrocarbon will be okay. So next, put it as a note. Rearrangement of carbocation. Rearrangement of carbocation. So here there is a chance for cis and trans, where trans is more stable. Okay, so if question like that, the maximum possibility, if the question is to find the major product in the elimination of 2-bromobutene, you simply look the choice, pen-2-ene, pen-1, then you can choose pen-2-ene. And moreover, you have to consider the base, whether it is bulky or non-bulky. Okay, usually non-bulky base are in the question. Okay, rarely a bulky base may ask. So in presence of bulky base, the mechanism may be different. That follows Hoffman's elimination, so that less substituted alkene will be the major product. Okay, but if they are asked to find the maximum possibility, then you should check the stereo arrangement also. Okay, fine. Rearrangement of carbocation. Okay, why the rearrangement means? To attain more and more stability. To attain more and more stability. To attain more and more stability. Okay, and you know a rough idea about the stability of carbocation. Which carbocation is more stable? Benzylic, then allylic, tertiary, second order, and there are some exceptions. Okay, I think, and it is this in your basic organic. Before that, there is CPM, cyclopropyl methyl carbocation, like that, propylium carbocation, OCC carbocation. So rearrangement of carbocation. The rearrangement is for attaining more and more stability. A primary carbocation may have a tendency to become secondary if possible. If possible. Okay, listen. So listen here. Should have a well idea about this one. If I have isobutyl carbocation, isobutyl, presently this carbocation is a primary, agreed. Presently this carbocation is a primary. Okay, then you simply check that if this positive charge moving to the alpha position, whether there is any benefit. If this positive charge move to here, what happens? It becomes tertiary. So here rearrangement is possible. Here rearrangement is possible. Okay, listen. If I have a molecule like this, okay. Presently this is a primary. If this positive charge, you simply consider the position, alpha position. If this positive charge is in this position, is there any benefit? Yes or no? Yes. So there will be a shift. There will be a rearrangement. First of all, you have to predict whether there is a rearrangement or not. Okay. Then only how the rearrangement. Okay. So here is a rearrangement. Because if this positive charge in this alpha carbon, then the primary become, here also the rearrangement. If this positive charge in this alpha carbon, then the primary become secondary. Listen. What about this molecule? Presently, what is the degree? Secondary. Okay. What about the alpha position? Alpha means anything just nearer to the specified one. Specified one, here it is carbocation. So this is alpha. This is also alpha. There are two alpha. So check if this positive charge is in this alpha position, is there any benefit? No. So towards here, there is no rearrangement. Okay. If this is in here, is there any benefit? No. Presently this is a, so if it is rearranged to here, so there is no benefit. So there is no rearrangement here, here, like that. Okay. First of all, you have to know whether a molecule can rearrange or not. Okay. Then how it is. Listen. This is a molecule with a primary carbocation. So here is the alpha position. So there is a chance for rearrangement. Okay. And now we are considering the rearrangement through shift. By means of shift. Shift like hydride ion, methanide ion, or pH minus ion, where the migratory aptitude, shifting tendency is much greater for hydride ion than CH3 minus than pH minus. Listen. So this is a shifting possibility. It may be hydride, or it may be methanide, or it may be phenide, or pH minus. So this is a present state of your carbocation, primary. So this is the alpha carbon, where hydrogen, what are the three valency in this alpha carbon? Hydrogen. What about the valencies in this alpha carbon? Hydrogen, methyl. So there may be a chance for the shift of. If this positive charge enters to here, we obtain what? Stability, right? If this positive charge is here, then somebody should move from this carbon to the, okay, ready? In order to have this positive charge here, then some kind of groups should shift from this carbon to this one. It may be H minus, CH3 minus, pH minus. If there is a competition, then H minus prefer the shift. So what about the groups in this alpha carbon? Hydrogen, CH3. So there is a chance for methyl or hydride shift. So which may take place? Hydride. Then let me show that. CH3. Let the CH3 here, or let the hydrogen here. Here is your CH3. Here is your CH2 plus. Now I am showing the hydride shift. Listen carefully. Hydride shift. Hydride shift means hydride, H minus. It's not H or H plus, H minus. H minus means the whole. If this hydrogen brings this electron, then it becomes H minus. This is H minus. This entire H minus shifted to this one. So what happens? If H minus or this electron taken from this carbon, then this carbon become positive. Agreed? And if H minus enters to here, CH2 plus H minus become CH3. Where the positive charge will be here. And this should be hydride shift so that you obtain a tertiary carbocation. Listen, tell me, CH3, here there is a CH3. Here it is CH2, where the CH2 become H. Okay, that's okay. CH2 plus become CH3, where the positive charge is here. Okay, since H minus shifted. Is that okay? So what is the benefit? It become a tertiary carbocation. Okay, wait. CH3, CH2, CH plus. What about the case? This is a primary. Is there any shift? Consider the alpha position and check if this positive charge is in the alpha position, is there any benefit? Yes. Consider the alpha position and check if this positive charge in this alpha position, is there any advantage? Yes. Presently this is a primary. If this positive charge here, then it become secondary. So there will be a rearrangement. Okay. For rearrangement, how many atoms are there? 3. What are they? 2 hydrogen and 1 methyl. So which one have a shift? Hydrogen. So here is a hydrogen. You know the shifting. H minus shifted to here, where the positive charge will be here. So H minus shifted to here, so that the positive charge to here. CH3, CH plus, CH3. Okay. So let me show the bond line of this one. Bond line of the very same molecule. You should be familiar in bond line also. Okay. So this is alpha carbon, where we have methyl and where hydrogen shifted. Okay. So what happens? It become tertiary. Ready? What about here? This is the present state. Agreed. This is the alpha, where hydrogen shifted to form secondary. Wait. I'll give you one more. What about the present neopentyl carbocation? Neopentyl carbocation. The present state is a primary, where this is alpha, right? If this positive charge in this carbon, is there any benefit? Yes. It become a tertiary. For this positive charge in this carbon, somebody have to move from here, right? Where the groups are only methyl. So only methyl. So there is a chance for methyl shift. If there is a chance for hydride and methyl shift, then hydride shift will dominate. Oh, this is, I'm sorry, this is the order. H minus, CH3 minus. Okay. What about the case? What about the case here? It's not CH3. CH3. With this electron also, this migrated to here, where here become a positive charge. Fine. Due to methyl shift, the entire shape of molecule may change. That is a speciality. Here will be the positive charge, right? Agreed. And here is the where the CH3 enters. The shape will be changed if it is a methyl shape. Shape of the skeleton chain may change. Listen, the shape is something like that, but it is now it is a third pentyl. So this is a case. Okay, but this is alpha. Presently, this is the very same molecule. The very same molecule. Okay, the methyl is shifted so that the methyl is here now, and here is the positive charge. The shape entirely changed. Where two methyls are in the same carbon, but now it is in a different carbon. Okay, that's a specialty of your methyl shift. Shape of the skeleton chain may change. Okay, I'll give you more examples. Copy this much. इधर Oh, sorry. That's okay. Fine. Thank you. So you simply show something like this, okay? Right.
it's good. It's good.
Oh, fine. CS2 plus. തെറ്റിയോ പിന്നെ ഷിഫ്റ്റ് പിനക്കോളും റീഅറേഞ്ച്മെന്റിലേക്ക് കാണുള്ളൂ, അവൻ പഠിക്കണ്ട. പിനക്കോളും റീഅറേഞ്ച്മെന്റിലേക്കാണ് അത് കാണുന്നത്. ഒന്ന് ടെക്സ്റ്റിലില്ല വെറുതെ. മൈഗ്രേറ്ററി ആപ്റ്റിറ്റ്യൂഡ് ചോദിക്കും. ഫീനൈൽ ഷിഫ്റ്റ് PH- അങ്ങനെ ഷിഫ്റ്റ് ചെയ്യും, വേറെ ഒന്നുമില്ല. എനിക്കുള്ള കാർബണിൻ്റെ അടുത്ത് ഫീനൈൽ ഗ്രൂപ്പാണെങ്കിൽ അതാണ്ട് ചാടും. മിഥൈലും ഫീനൈലുണ്ട്, ഫീനൈൽ ചാടും എന്നാണ് പറയുന്നത്. PH- ആയിട്ട് ചാടും, ഇവിടുന്ന് അങ്ങോട്ട് ഇവിടെ പ്ലസ് ആവും. ഷിഫ്റ്റൊക്കെ ഒരേപോലെ തന്നെ. H- പോയാൽ അതേപോലെ തന്നെ CH3- പോയി. CH3- പോകുമ്പോൾ പാരൻ ചെയിന് മാറ്റം ഉണ്ടാവുന്നുള്ളൂ. അതുപോലെ PH- പോകുമ്പോൾ പാരൻ ചെയിൻ മാറും, കാർബൺ മാറുന്നുണ്ട്. Okay, first you have to check whether a shift or rearrangement possible or not. Okay, then hydride or methyl. Usually we have hydride or methyl. Okay, in a rare case there will be a possibility for phenyl shift. And this is very important for hydrocarbon or the reactions of alkane. Or is there any carbocation intermediate in any reaction? There may be a chance for rearrangement. Like your SN1E1, rearrangement is possible. This is a rearrangement. Okay, that's very important. Is there any possibility for shift? What about the degree of first? So what about the alpha? This one. If this positive charge in this alpha carbon becomes secondary, so there is an advantage. So there will be a chance for shift. And you know, H minus shifted to here to become positive charge on here. Keep it in mind and make this as a secondary carbocation, okay? No need of showing H minus too, okay? Ready? Keep it in your mind. H minus may shift to here so that the positive charge will be here and make the rearranged version, okay? No need of showing H too, okay? Ready? This is not required. Can show. That's up to you. If you want, can show. Otherwise, you simply cancel. You should have a clear idea whether the shift is possible or not. If so, how? Okay. So it become a secondary, right? Agree, fine. What about this one? This is a secondary one, right? This also, this alpha is a, this alpha is also, so no need of rearranging. So no shift, no rearrangement. Okay? The next, this is alpha. I'm sorry. Alpha. Okay? This is a tertiary alpha, agreed? This is secondary alpha. Presently it is a secondary. So there is a chance for tertiary. Listen. This carbon has two different groups. What are they? Hydrogen and methyl. So there is a chance for hydrate shift. Okay, so that H minus to here, the positive charge will be on that carbon, the forms a tertiary carbocation. Okay. What about the next? Presently a secondary. And this is a tertiary alpha. So if this positive charge in this tertiary alpha, it will be more stable. For that, somebody have to shift from that portion. There is no hydrogen, only methyl group. So your methyl group shifted to here. Is it okay? Well, the shape may change. Okay. Before the shift, two methyls are in the same carbon. Now it is in a different carbon. Okay, that's a special importance of your shift, methyl shift. The next is this one. Presently it is a primary. This carbon is a primary. What about the alpha? There is only one alpha, and this is the alpha. Where if the positive charge is here, it become tertiary, right? So somebody have to shift from that tertiary position, and it is clear that we have hydrogen too. Okay, so H minus may shift to here to form this one. Okay. Ready? What about the next? This is presently a, and this is also an alpha position. Right? No shift. Here it is a secondary. This is a secondary. So there is no benefit once it is shifted. So there is no rearrangement. Okay. What about the next example? Listen. Next example. This is secondary, right? This alpha is a primary. This alpha is a allylic secondary. Allylic secondary is somewhat stable than normal secondary. Okay, so there is a shift. Okay, you should have an idea about the stability of carbocation. So there is a chance for shift, so that we obtain a more stable allylic secondary carbocation. So what do you mean by allylic? An alpha position with respect to a double bond, right? Fine. So H minus shifted to here. Okay. Ready? What about this one? This is presently a primary. Here we have hydrogen. This is alpha position. It is a tertiary. But this is extra stable. Okay. Extra stable due to dancing resonance. Dancing. And this molecule have a resonance structure or something like this. Which is referred as dancing resonance. Cyclopropyl methyl carbocation, CPM. And this molecule have a dancing resonance, something like this. That's why it is extra stable. If the positive charge in this position, okay, it is nothing but, listen, this sigma bond is a weak sigma bond since the due to angular strain. Actually, the carbon is an sp3. Listen, actually the carbon is a sp3 carbon. So the expected bond angle is 109 degree. But in case of cyclopropane, the angle is only 60. So this is a high angular strained bond. So easy to cleave. Since there is a positive charge in this carbon, this bond may cleave. Okay, due to high angular strain, this bond is a very weak bond. So this is cleaved to jump the electron to here. Hey, this electron may be like this. This sigma bond cleave to delocalize like this. So here will be the positive charge. Here will be there is a section. There is a chance for from here or from here. If it is from here, will be like this. If it is from the top, will be like this. And the structure is something resemblance to dancing like structure. That's why it is said to be dancing resonance. Okay. So there is a high chance for this delocalization because this bond is very weak. So there is a high chance for the stabilization of this positive charged carbon. Ready? Due to this resonance. That's why its stability is much greater than benzylic. So the CPM carbocation is already stable. So there is no need of rearrangement. Even it is primary. Even if it is primary, it is extra stable. So no need of rearranging. Okay. So the rearrangement is purely based on the stability of carbocation. So you have a clear idea about the stability. Okay. Rearrangement may be okay. First rearrangement followed by the second rearrangement is possible. Okay, for that we can consider these two examples. Okay. What about the first? What about the first? This molecule. Repeated rearrangement may be possible. Rearrangement followed by rearrangement is possible. Listen, this is primary. Okay, repeated rearrangement may be possible, but every step have an advantage. Then only it rearrange. Okay, first step should have an advantage followed by advantage. Then only it may rearrange. So this is a primary, right? If this positive charge in this alpha carbon, what happens? Secondary. So there is a shift from hydrogen, right? So it become what? Okay. If this positive charge in this alpha carbon, what happens? Tertiary. So there is an advantage. So next shift also taking place. Okay, take place. So in the sambhagya H minus will be like this. Okay. What about the next? Here. What about this molecule? This is presently secondary. If this positive charge on this carbon, what happens? Tertiary. Okay. If this positive charge in this carbon, it become tertiary. Before that, this positive charge should be in this carbon, right? That is not possible. Okay. We can say that it is stable if this positive charge in this carbon. Okay. There is a chance for shift followed by shift. But the first shift is not feasible. Why? This is presently a secondary. Then why to rearrange for the next secondary? Okay, but here it is possible. Why? Primary become, then become. So there is a clear advantage. Okay. So here there is no rearrangement. Okay.